Okay, let's talk about repeating decimals. Let's take a look at this first example here. This says 2 divided by 11. So first off, make sure that you set this long division up correctly. Your students will almost invariably, until they truly understand, they're going to want to put the small number on the outside and the big number underneath. So be careful and make sure that your students understand. Okay, so here it looks like we're going to have a decimal. So I'm going to put my decimal point here. 11 goes into 20 one time. 1 times 11 is 11. Subtract here. We have 9. Going to have to bring down the 0. 11 goes into 90 8 times. 8 times 11 is 88. Bring it down. We have a 2. Now, we can do this as many times as we want to. Excuse me. But the way that this works is once that original dividend comes back up, then we're going to repeat the pattern. Okay? So this, if we were going to continue, would continue with a 1, and then an 8, and then a 1, and then an 8, and so forth infinitely. Henceforth, the repeated decimal. Now, the way that we note this answer is we would say, putting in your leading 0.18 with a bar across that 1/8 to indicate that those are the repeating decimals. So the block of repeating digits behind the decimal is called the repetend. So this is the repetend. And the length of the repetend is called the period. So here the period is 2. Over here on our example of 0.373737, blah, 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 that has a period of 2. And you can't see it because I'm actually personally in the way, but this does stop at the 2 here. So this is just a period of 1. Now, for clarity, you don't want to write this, so we're not going to write it like this, even though that is actually true, but that messes up the period, and the period is important. So it is important for you to instruct your students and correct them when they do it incorrectly, that it is actually just 1, 2, because it's the same digit repeating over and over again. Representing repeating decimals as rational numbers. Okay, this should have been bolded, so I'll just underline it. So the trick here is kind of tricky. Once you understand how it works, it kind of makes sense. But in the beginning, it seems like it's some kind of insane voodoo. So let's just take something we already know. I think we commonly all know that infinite is equal to 1/3. I think we already know that. So I'm just going to establish that for this example's sake. So what we're going to do is we're going to let n equal the repeating decimal. So whatever we're evaluating, we're going to let n equal that. Now, the idea is to remove the repeating digits. And remember, the rules of the way our math works is that if you do one thing to one side of an equation, a proportion or whatever, you have to do the exact same thing to the other side. So if we start off with our n is equal to 0.3, the plan is you want to multiply n by whatever power of 10 to get the repeating decimal a whole number and the repetend, or the repetend, yes, repetend is directly to the right of the decimal point. So I'm going to do a couple more examples, but this one to get us started. So notice here we started out with 0.333333, right? And so when we multiply it by 10, it moved that decimal point over so that we have a whole number and now a whole bunch of 0.33333333 forever, right? Okay, so we're going to just use this algebra trick, and the algebra trick says that you move it so you have a whole number with a repeating decimal after it. That is the same as n. So the repeating decimals, so the decimal parts here have to be the same. So the decimal parts must match, okay? So once you have the decimal parts that are the same, then we can subtract them here. So I wrote the 10n is equal to 3.3, which is true. If n is equal to 0.33333, then 10 times n is 3.33333. We know that. We do the subtraction. We get 9n is equal to 3. And then we solve this by dividing both sides by n, and we get what we already know coming into it, which is it is 1/3. So this is the way that you convert a repeating decimal into a rational number. So let's look at another example. So this next example here, you can see first off that the repetend is directly right of the decimal point. Okay, so we don't have to do anything crazy about that. Notice over here it's not yet, so we'll have to do a couple of extra steps. Now we have to multiply, so the first thing we do is we multiply by the power of 10 to move the decimal 1 period. Okay, so here we know the period is equal to 3, so we're going to use 10 to the 3rd power, or 1,000. Okay, so that's how we decide what number to multiply here by. So we're going to let n equal 0.235, repeating, and we're going to say 1,000 n is equal to 235.235, still repeating. Now we can put that together for our equation, and of course we're going to take the large number on top here. So we have 10,000 n is equal to 235.235 repeating, minus our original n, which is n is equal to 0.235. Now you can see how this trick works. We're going to eliminate the repeating decimals. All right, so now we get to do that math here, and this gives us 999 n is equal to 235. I find this to be a pretty cool trick. dividing by 999 on both sides. We get n is equal to, and I think this might reduce, let's see, no, it does not reduce. So n is equal to 235, 8, 9, 10, yeah, doesn't reduce, over 999. And you can check this, right? You can put this in your calculator and give it a check and see what you see. All right, now this one's a little bit different. This one, you have to notice that over here on the left, the decimal point was right here, and then we had the repetend started. But here we have 2 spots before the repetend. So the first thing we have to do is move the decimal and we want to move the decimal 2 spots. So 2 places. So that means we're going to multiply by 100. Okay, so that's the first thing we're going to do. So we're going to start off with 0.2345 here. Make sure I'm writing this out the right way. Oh, okay. Sorry, I typed it up a little bit differently than my example in my notes, but that's okay. We'll go for it. So here, what we need to do is we need to multiply this by 100. If this guy's n, so 100n is equal to 23.45. Repeating. Now, that hasn't taken care of the next step. So now we're going to pick up here and multiply by the power of 10 to move the decimal 1 full period. And what we know here is that our period is equal to 2. So we're going to say 100 times this stuff up here, 100 n, and that's going to equal 2345.45. Notice what we did was it takes more than just turning it into a whole number, because we have to be able to remove that repeating part. So this is what we wind up with on this end. And now we can put the math together and do the subtraction. So let's see, that is 10, 1, 2, 3, 4, so 10,000 n is equal to 23,045 and 45 hundredths repeating. And then we're going to subtract, and now we have to be able to subtract off. Remember, we're trying to get rid of the repeating part. So we're going to have to use our 100 n. If we use just regular n, which is what this guy is here, sorry I didn't write n. If we use just regular n, then it's not going to get rid of all that repeating stuff. So here we go, negative 100n is equal to 23.45 repeating. Now let's see what we have here. 0099. n is equal to, and check this out, these guys cancel off because that's 0.4545454545 forever minus another 0.45454545 forever. So yay, we got rid of that, and then we just need to handle this business here, and this gives us 2322, and divide both sides by 9900, and n is equal to, I'm going to have to bust out the old calculator here. Well, we can divide it, we can divide both of them for sure by 2. I'm sorry, it's been a long day and my brain is fried. And since I made the mistake by writing the problem down wrong, I'm not prepped. So we'll just pull out the old calculator and save me and me trying to do this real quick. I'm just gonna this breaks down to 129 over 50 after it's all said and done. Oh wait, no, sorry, it didn't seem right. I messed up there. Dropped one of my 9s off. I mean, one of my 0s off. Didn't seem reasonable. 550. Okay. And then you can check that if I go 129 divided by 550, because now I'm all in my head. Yes, 234545454545. Yay, I did it right. Okay, excellent. If you have any trouble, let me know. You can always go back and do it. I suggest that you write these problems down and try to emulate it. Write down steps in your own words while you're going through. They might not be steps that you would write down for your students, but they will be steps for you to understand what's happening from one step in the process to the next. So work on it. Don't get frustrated. There are some interesting conclusions when we do deal with repeating decimals, and one of them is the fact that 0.999999999999999 is actually 1. And we can prove it here. This is us justifying it using the same way that I did just a moment ago with this technique right here, where we move the decimal place one time by multiplying by 10 and then subtracting and then solving the equation. And remember, we're subtracting off the repeat, the repetend. I totally messed that up. R-E-P-E-T. I want to mess that up pretty good. It's not one of those words you use very commonly in your normal vernacular, you know, so it's a little hard. Okay, so look here. This proves that this is equal to 1. Let me show it to you another way. Here's another way we could look at it. We could add 1/3 and 2/3. Well, we know 1/3 plus 2/3 is equal to 1, but we can write it out as a repeating decimal and add it together as a repeating decimal. So that does show also that 0.9 repeating is equal to 1. And then finally, I thought this one's really clever. And this idea will really help us when we start doing the percentages. If we know 1/9 is 0.1 repeating, so we can just work that out, find what 1 repeating is, and then we can just scale that out. So 1 is equal to 9 times 1/9. We know that, right? Because the 9/9 is equal to 1. So 9 times 0.1 repeating is equal to 0.9. So this all works. So 1 is equal to 0.9. Kind of cool. And then we're going to end, because this one is quite short, which is lovely. We're going to end with ordering repeating decimals. So we do this the same way as we compare terminating decimals. We line up the decimal points and compare them digit by digit until the greater one can be determined. It's just really just that straightforward here. And so I've got 2 examples here. Now, one thing I do want to caution you on is one of the biggest student mistakes is that they see that 7, 8, 2, 1 is bigger than 3, 4, 7, 8. They focus just on that repetend. So it's really important that you line it up and you kind of go through it. 1 and 1 are equal. 3 and 3 are equal. 4 and 4 are equal. 7 and 7 are equal. 8 and 8 are equal. Here, 3 is greater than 2. Therefore, 1.3478 is greater than 1.347821. Another thing that your students might equate is this one is longer than the original, and so you need to dispel that kind of idea and make sure that they understand when there is a line over it, neither one is longer. They're all equally the same length because they're infinitely long. Okay, well, thanks. I'll see you next time.